Today we'll be working with the L298N H-Bridge motor driver. You'll learn what an H-bridge is and how to use the inexpensive L298N module with an Arduino to control the speed and direction of a pair of DC motors. We'll even build a simple robot car that you can control using a joystick. So stay tuned and welcome to the workshop. Hey, welcome to the workshop. Today we're going to be working with DC motors and we're going to be controlling them with a component called an L298N H-Bridge. We're going to look at how DC motors actually work and even a tiny bit of the history of them because I think that stuff's interesting. Then after that we'll discuss what an H-Bridge is if you're not sure of that. Once we do that, we'll examine the L298N. The L298N is a really common H-bridge module that you can use on its own or with an Arduino, and we're going to be doing both. After we do a couple of experiments with it, we're going to actually do something amusing and build a little robot car that we can control with a joystick using an Arduino and an L298N. So let's get at it. Let's take a look at DC motors. DC motors are motors that operate on direct current, as opposed to motors which operate on alternating current. The first motor was invented by a Hungarian physicist named Ányos Jedlik in 1827, and he called his device an electromagnetic self-rotor. Interestingly enough, the self-rotor that you see pictured here was constructed in 1827 by Jedlik, and today can be found in the Museum of Applied Arts in Budapest, and the device is still working 190 years after he constructed it. Now, the self-rotor wasn't a particularly practical motor. The first practical motor was invented in 1832 by a British scientist named William Sturgeon. DC motors are available in several different configurations, from tiny little motors to absolutely huge ones. Small DC motors are very inexpensive, and therefore these are ideal for hobbyists just like us, for all of our little contraptions. We can use DC motors to construct robot bases. They can be used to create quadcopters. They're also often used in model planes and boats, and a myriad of other applications. So how exactly does a DC motor work? Well, here you'll see a diagram of a very simple DC motor. The shaft of the motor, the part that does the rotating, is referred to as an armature. And on the armature you will see a couple of coils of wire. These coils are connected to the commutator. That's that little copper ring at the very front of the armature that you see. The connections to the commutator are called the brushes, where the positive and negative voltage are applied. On the outside of the motor, you'll see a couple of permanent magnets arranged in opposite magnetic polarity. Now, when DC current is applied to the commutator, it sets up a magnetic field inside the coils. The coil magnets interact with the permanent magnets, causing the armature to rotate. Now, as the armature rotates, the polarity is continually reversed, causing the magnetic field to be reversed and the rotation to continue. This type of a motor is referred to as a brushed motor, as opposed to a brushless motor. And this is the type of a motor that we will be experimenting with today. So let's take a look at how an H-bridge actually works. In order to simplify things, I've drawn an H-bridge using 4 switches. In real life, the switches would probably be replaced with transistors, although you could build an H-bridge with switches if you really wanted to. Now, why is this thing called an H-bridge? Well, if you look, you can distinctly see a letter H in the configuration with a motor sitting in the bridge part of the letter H, thus the term H-bridge. So how does this all work? Well, you have a positive voltage applied to the top of the H-bridge circuit and a negative voltage applied to the bottom. Now watch what happens when we connect these two switches. The positive is applied to one side of the motor and the negative to the other side, and in this case our motor will spin clockwise. Now let's take a look at what happens when we close the other two switches. You will see that a negative voltage is now applied to the one side of the motor and a positive to the opposite side, causing our motor to spin counterclockwise. This is how an H-bridge functions. Now there are a couple of different styles of L298N modules that you'll run across, and I wanted to show you the differences between them. They work exactly the same, and you can use either of them in the experiments that we'll be doing, but I just didn't want anyone to get confused if their module didn't look like the one that I was using. So here's the one that I'm using, and you'll see all of the digital inputs with the enables on either side of this connector. Here is another common module, and here are the digital inputs. The enables are actually here and they're jumpered, so they're always enabled, but you can just pull those jumpers and use them exactly in the same way. There's also a 5-volt jumper, which I've got off on my module. It's over here. The 5-volt jumper on this common module is over here. Then the motor connections. The two green connections on this module are motor A and motor B. You will find two connections on this module for motor A and motor B. And finally, the connections to the 5 volts, the 12 volts, and the ground are all done in the middle of this module here, whereas on this module you'll find those same three connections on this connector. So otherwise these modules are identical, and you can use either one for these experiments and they'll work perfectly fine. Let's take a close look at the L298N module. Now, the module that you have may be physically different than the one that I'm showing here, with the connectors in a different position, but they'll be labeled the same and they'll function identically. Now first we'll look at the power connections. There's an input for the motor power, which can be anywhere from 5 to 35 volts. There's also a common ground, which is common to all power supplies. Then there's a 5-volt input. Now this 5-volt is to drive the logic circuitry on the board, and it's actually optional. It's possible to use the motor power to also supply the 5 volts. After that, we have two connections for our motors, motor A and motor B. Now here's the jumper that we use to select whether we're using the optional 5-volt supply or whether we are using the internal one. In this illustration you can see that the jumper is open. I've just got it hanging there. So we are using the optional 5 volts input in the way I've shown it. After that, we have the logic inputs to the controller. There are 3 logic inputs for motor A, the enable line, input 1, and input 2. And then motor B has the similar connections, enable, input 3, and input 4. Now here's how the inputs work. I'll show you motor A. Motor A's enable line, when set to 5 volts, enables the motor. When it is grounded or set to logic 0, the motor is disabled. It can also be fed pulse width modulation signals, and this can control the speed of the motor, and we'll talk about PWM in a few minutes. Now motor A's input 1 and input 2 work as follows. If you apply 5 volts to input 1 and ground to input 2, the motor will spin in a forward direction. If you reverse that and apply ground to input 1 and 5 volts to input 2, the motors will run in reverse. And of course the motor B inputs work in exactly the same way. Now pulse width modulation may sound like a complicated technical subject, but when it comes to controlling motors, it's actually pretty easy to understand. We simply send a series of pulses to the enable line on our motor. The wider the pulses, the faster the motor will spin. So for example, if we send a series of short little pulses to the motor will spin slowly. If we increase the width a bit, the motor will spin faster. Increase the pulse width a bit more, and the motor will spin even faster. If we want to bring the motor to a stop, we'll just stop sending pulses and hold the enable line low. This will disable the motor. If, on the other hand, we want the motor to run at full speed, we'll stop pulsing it and hold that line high, and this will cause the motor to be enabled constantly and spin at full speed. In order to show you how the L298 works, I've set up a little experiment on my workbench. What I've done is I've taken my L298, I've removed the 5-volt jumper so that I can power this with an external supply. I've connected a power supply to it. What I've done is I've used a little buck converter that has reduced my 12-volt power supply down to 7.4 volts. Now you might be wondering why 7.4 volts. Well, the reason for that is that the two transistors that act as switches in the L298 are each going to have a voltage drop of 0.7 of a volt. So what I need to do is apply 1.4 volts more than my motors actually require. And since these are 6-volt motors, I have given it 7.4 volts. In addition to the 7.4 volts, I've attached a 5-volt power supply, and I'm just using my bench supply for that for now. I've attached two motors to it, motor A and motor B, and I've also run the 5 volts over to my solderless breadboard. At this point, I've then taken all of the inputs from the L298 and wired them up to the breadboard so that I can experiment with the inputs and send them to either ground or 5 volts. Okay, for the first experiment, this is how I've wired the inputs. I've set enable 1 to 5 volts, which is a high. Input number 1 is also at 5 volts, and input number 2 is at ground. These are the lines that control motor number A. For motor B, I've taken input number 3 and set it to 5 volts. Input number 4 has been grounded, and enable number 2 has also been grounded. So when I do this, what will happen is that motor A will move forward. Motor B, however, won't move at all, and that is because its enable line is set to ground, and you can see that as follows. Okay, for the second experiment, I'm going to take enable 2, which controls motor B, and I'm going to move it high as well. In this case, both of our motors will move forward. Next, I'm going to reverse the inputs for motor number A. So I'm going to take input number 1 and ground it, and input number 2 and bring it to 5 volts. This will cause motor A to run in reverse, while motor B still runs in the forward direction. And last but not least, I've taken both of the enable lines and grounded them. So enable number 1 is grounded, and so is enable number 2. In this configuration, both motors will simply be off. And as you can see, they are. So now that we've shown how the L298 works with a breadboard, let's add an Arduino to the equation and see how we can get it to control the speed of the motor as well as the direction. So let's bring an Arduino into the picture. I've taken away the 5-volt power supply, and I've used the 5 volts and ground from the Arduino Uno to power the L298N logic circuits. I've hooked the inputs of the L298N to a series of the digital outputs in the Arduino, and the hookup is as follows. I've taken the enable 1 line on the L298 and connected it to digital output pin 9 on the Arduino. Input 1 on the L298 is connected to digital output pin 8. Input 2 is connected to output pin 7. Input 3 to output pin 5. Input 4 to output pin 4. And the enable 2 line on the L298 is connected to the Arduino's digital output pin 3. Again, you could use different output pins on the Arduino if you're willing to modify the sketch, but just keep in mind that both of the enable lines need to be connected to a digital output pin that is capable of pulse width modulation. So let's look at our Arduino sketch to do our motor demo. Now we're going to start off by declaring a number of integers for motor A and for motor B. And these are just the inputs to the L298N. The ENA and ENB are the enable lines for motors A and motor B, and then IN1, IN2, IN3, and IN4 are simply inputs 1, 2, 3, and 4 to the board. Now again, you could use different pin numbers if you wish, by just defining different numbers for these integers. However, keep in mind that enable A and enable B have to use pins that are capable of pulse width modulation. Pins 9 and pin 3 are capable of PWM. So if you're changing this, keep that in mind. After we've defined these integers, we're going to just go through the setup routine and set all of them up as outputs, because all of these are outputs from the Arduino, because we're feeding these into the L298Ns. Then we're going to start with one of two functions. Our first function is called Demo1, and Demo1 will run the motors in both directions at a fixed speed. So the first thing we're going to do is we're going to turn on motor number A with the input 1 and input 2 lines. Then we're going to set the speed of motor A. We're going to be using the analog write command. Now analog write will write pulse width modulation signals out to PWM enabled pins on the Arduino. And it can have a range of 0, which is basically off, to 255, which is full speed. We're going to set these to analog write to 200, so it's going to be near full speed but not quite. And then we're going to do the same thing for motor B. We're going to set it on in one direction, and we're going to set it to also do an analog write of 200. Now we're going to run the motors at that speed for 2 seconds, so we put a delay of 2000 milliseconds in here. And then we're going to change the motor direction. So we're going to take inputs 1, 2, 3, and 4 and set them to reverse the motor. So we do that over here. And then the motor will continue to run at the speed of 200 because the analog write is still 200. We do that for 2 seconds. And then we're going to turn the motors off by setting inputs 1, 2, 3, and 4 all to a value of low. And that's basically our first demo. Now we have a function for demo number 2. And what this is going to do is it's going to run the motors across all the range of possible speeds. It's going to run it up to the full speed and then run it down to low speed. So first of all, we're going to go and set the motors on again in the forward direction. So we set inputs 1, 2, 3, and 4 accordingly. And then we're going to take a loop and accelerate it from 0 to maximum speed. Now in this loop, we're going to take an integer we call I, and we're going to loop it between the values of 0 and 255. And so we're going to do an analog write to enable A and enable B. It's going to start off with these values being 0, and then we're going to delay it for 20 milliseconds, then it's going to increment it, and the values will be 1. It'll delay for 20 milliseconds, etc., all the way until it gets up to 255. Once we do that, we're going to do the opposite thing. We're going to run a loop, except we're going to decrement it. So this is the same thing, except we're starting at a value of 255. We're working our way down to a value of 0, and we're decrementing the loop. And so again, we're going to start off with an analog write of 255 to each of the motors, delay by 20 milliseconds, and then go to 254, delay by 20 milliseconds, etc., until we get down to 0. And then finally, we're going to write digital writes to all of the pins low again to turn off the motors. And so now that we've defined our two functions, in the loop all we simply do is we run demo 1, and then we delay it for a second, and then we run demo 2, delay it for another second, and then the loop repeats itself infinitely. So this is basically our motor demo. So let's take a look at it working. Alright, I've loaded the motor control sketch onto my Arduino, and I've temporarily unplugged the USB cable from the Arduino because this sketch will start immediately as soon as the Arduino is powered up. Otherwise, everything's connected up. I've got my power supply connected to the L298N board. The motors are connected to it as well, and the board is connected to the Arduino. So as soon as I power this, it should start our demo sketch. So let's take a look at that. And it runs through it. You see it'll repeat it. It starts by going forward, then it goes backwards, and then it gradually comes up to speed, and then it gradually reduces speed. And so that's our demo sketch. Now let's expand upon our circuit and connect a couple of potentiometers or variable resistors up to the Arduino Uno. This will allow us to manually control the speed of each motor. Now the value of each of these potentiometers is not particularly important. As long as they are 10K or higher, they should work. You also want to get linear taper potentiometers, and these are the most common type anyway. Now one end of each pot is connected to the ground, and the other end of it connected to 5 volts. In my hookup, I used a solderless breadboard to simplify the connections, although that isn't illustrated here. The wiper of each pot is connected to one of the analog inputs on the Arduino, and I connected pot A to analog input 0 and pot B to analog input 1. Again, if you wish to use different analog inputs, that would be fine. You'll just need to modify the sketch accordingly. So now that we've hooked the 2 potentiometers up to our Arduino, let's take a look at the sketch that we're going to be using. Now our sketch starts off in the same way as the last sketch. We define a number of integers for the output pins on the Arduino that we're using as inputs to the L298N. Then we've got a couple of new integers over here, speed control 1 and speed control 2. And these are defined as A0 and A1. These represent the analog inputs in the Arduino. Now if you wanted to use 2 of the other analog input pins, just change the value of A0 and A1 and you can do that. Now we have another couple of integers we've defined, and these are motor speed 1 and motor speed 2, which represents the speeds of the 2 different motors. We'll initialize these with a value of 0. Then we go into the setup, which is identical to the last program. We set all of the digital outputs and define them as outputs. We don't need to set the analog inputs up as inputs because by nature they're already inputs. Then everything is happening in the loop. We'll set the motors to a forward direction by writing to the IN1, IN2, IN3, and IN4 pins. And then we're going to read the values from the potentiometers using the analog read command. Now the analog read function uses the internal analog to digital converter that's built into the Arduino. This is a 10-bit analog to digital converter, so we're going to get values from 0 to 1023. Now, if you recall, when we do an analog write to send pulse width modulation out to our enable lines, we can take a value from 0 to 255. So we've got to convert this range of 0 to 1023 to a range of 0 to 255. And there's a couple of ways we could have done this. One way would have simply been to divide these values by 4, and that would have actually worked just fine. But I chose to use Arduino's map function, and if you haven't used the map function before, it's a good function to get familiar with. What map does is it takes one range, in our case 0 to 1023, and maps it out to another range of 0 to 255. This really works well when you have 2 ranges that don't evenly divide into each other. And so I've set motor speed to be mapped to a value of 0 to 255. And then the last thing I do here is I have found that the motors actually started to buzz when I got to a very, very low value. And so what I've done is I've simply included these if statements, and in the if statements I say that if the motor speed is anything less than 8, then we'll just call it a 0, because the motors aren't moving down at that speed anyway. They're just making an annoying buzzing sound. You may want to adjust this value of 8 to suit your own particular motors. And then finally we do an analog write of motor speed to enable A and enable B, and that sends the pulse width modulation out to our motors. And this is in the loop, so it just continues to repeat, read our potentiometer values, and send the values out to the two enable lines. And that's it for our sketch, so let's watch it in action. Okay, now that we've hooked up the two pots and loaded our sketch, let's try it out. We'll turn the pot for motor number A, and I can adjust its speed. And motor B, same thing. So now that we've seen how we can use two potentiometers to control two motors with an Arduino, let's take it a step further. Our two motors, you've noticed, have been mounted onto a robot car base. And what I'd like to do is actually drive this little car around the room. Now, two potentiometers are going to be a very difficult method of controlling a car, plus I have no method of actually reversing it. So what I've decided to do is replace the two pots with a joystick. Now, a joystick essentially is just two potentiometers, one that controls the vertical or y-axis, and the other one that controls the horizontal or x-axis. A joystick also contains a momentary contact switch, but we're not going to use that in this particular hookup. Now let's take a look at how I've hooked the joystick up. Essentially what I've done is just replace the potentiometers with it. A joystick also has two pins, one labeled VCC and one labeled ground. I've connected VCC to my 5-volt power supply from the Arduino, and I've connected the ground, of course, to the ground line. Now the vertical output I've connected to analog input A0, and the horizontal output is to analog input A1, again just the same way I had the potentiometers. Now what I've done is I've arranged the joystick so that when I push the joystick forward, the motors will drive the car forward. When I pull it backwards, the motors, of course, will drive it backwards. When I move the joystick a bit to the left, the car will steer to the left. And when I move it to the right, it'll steer to the right. As you can see over here, I'm going to push the joystick forward, and there go my motors. And when I pull it backwards, they go the other direction. If I move it off to the left, one motor spins faster than the other. And when I move it to the right, the opposite effect occurs. So now that we've looked at that, let's take a look at the sketch that makes all of this possible. And then we'll take a spin with our little car and drive it around the room. So here's the sketch I've come up with in order to control my little car with a joystick. Now, as with all the other sketches, you can find these on dronebotworkshop.com along with a complete explanation of each sketch. But I'm going to go over this one with you right now. Now, we start off the same as we have with our other sketch. We've defined a number of integers, and these are for the inputs and the enable lines to the L298N. Then we've got the analog inputs of the Arduino, which I've mapped out to JoyVert and JoyHors for the vertical and horizontal potentiometer in the joystick. As with our last sketch, we define a couple of integers to represent the motor speed for each motor, and we initialize them at 0. We've also got a couple of new values here for the vertical and horizontal positions of the joystick, and they're initialized at 512. Now remember that the analog to digital converter in the Arduino will convert the input voltage to values between 0 and 1023, so 512 is pretty well in the middle of the range. Then in the setup, we go and initialize our pins as outputs as we did before, and we'll also start our motors off both disabled with enable A being low and enable B being low, and also set so that the motors will spin in a forward direction. Then we go into the loop. Now we're going to get the joystick positions and put them into the values that we defined for joystick positions using an analog read command, just like we did with the potentiometers in the last sketch. Now remember, the vertical joystick is the one which determines whether we're going forwards or backwards. If we push it all the way up, we want to go forwards. If we pull it all the way back, we want to go backwards. Also, the more we push it up or the more that we pull it down, the faster we want to go. So we're representing both speed and direction with this joystick. Now, the vertical position will be above a value of 512 if we want to move forward, and it will be below 512 if we want to go backwards. However, we have to consider that most joysticks are not perfect, and that the variable resistors or potentiometers inside them have a little bit of a tolerance. So I've allowed about 10%, and I've decided that any value above 564 means that we want to go forward, where a value of below 460 determines we're going backwards. So in the first case here, I evaluate for values below 460. We want to go backwards. We'll set the motor directions backwards, and then we'll go and determine the motor speed. Now in this case, as we pull the joystick down, the numbers we're reading on the analog input are going to get lower and lower, yet we want our motor to go faster and faster. So we need to do a bit of math. So I take the value and I subtract 460 from it. That's going to give me a negative number. And so what I need to do is multiply that by -1 in order to make it positive. Then after that, I use the map command, as we've seen before, to map the values between 0 and 460 to values between 0 and 255, so I can drive my motors with pulse width modulation. Now, in the case where the vertical potentiometer is reading above 564, we are going forward. So again, we'll set our motor direction to forward, and we'll determine the motor speed with a map command. We don't need to do the fancy math we did before, because as we push the joystick forward, the values are going to go up and up. So we'll just map the values of 564 to 1023 to values between 0 and 255. If it doesn't evaluate to either of the previous two conditions, then the motor's stopped, and we'll set the motor speeds to 0. Now we'll do the steering, and we do that with the horizontal potentiometer. Again, we use the criteria of below 460 or above 564. If it's below 460, we do basically the same thing we did before. We do the mathematics and convert it to a positive number. And then we'll map that position to a value between 0 and 255. Now, we do a little bit of math after this, because remember, when we want to turn left, what we want to do is spin the right motor faster and spin the left motor slower. So motor number 1 is our left one, and motor number 2 is our right one. So on motor number 1, we actually minus this value from the current motor speed, which we determined earlier. On motor number 2, we add the value to it. So we make motor number 1 go slower and motor number 2 go faster. Now, this will likely produce a value in many cases that exceeds 255 or goes below 0. So we have a couple of if statements here. If the motor speed is below 0, then it's equal to 0. Whereas if the motor speed is above 255, then we'll equal it to 255. Now, if the horizontal is above 564, we want to turn right. And we basically do the same thing. We'll map the values, and then we do the same math to add and subtract. Only now you'll notice that in this case we are adding to motor speed number 1 and subtracting from number 2, because this time we want to turn right. Again, we make sure we don't exceed the values of 255 or 0. Finally, I have the same statement I've always had to prevent the motors from buzzing. If the motor speed is less than 8, then we'll just consider it to be 0. And last but not least, we use the analog write command to write to the enable lines on both of the two motors to spin them at the correct speed. And then the loop just repeats itself as long as the Arduino is powered up, and we can drive our car around the room. So now it's time to give our little car a test drive. As you've noticed, I've put a very, very long wire between the car and the L298. And that's, of course, so I have a little bit of space to maneuver the vehicle. So I'm going to stick this down on the floor and see if I can drive it best as I can. I'm going to move the joystick forward, and our car moves forward. If I move it backwards, the car moves backwards. I'm going to move it a little off to the right, and move a little off to the left, and so I can steer the car too. It's not that practical with this wire on it, but as you can see, it's actually a working little robot car. Now, who said Arduinos can't be fun? Okay, so that about does it. We've learned quite a bit in this video, haven't we? We've learned what a DC motor is, how it works, even a little bit about the history about DC motors. We've learned how an H-bridge works, and how we can use the L298N H-Bridge controller with an Arduino, and even without an Arduino, to control a pair of motors. We've taken that knowledge and we've even built this cool little robot car that we can drive around the room using a joystick. So I think we've covered quite a bit, and I hope you've enjoyed it. If you did enjoy it, please consider subscribing to the channel, and if you have any comments, please leave them below the video. If you need the code for any of these projects, visit dronebotworkshop.com, where you'll see a detailed article about everything we've covered, as well as all the sketches you'll need in order to recreate all of these experiments yourself. So thank you once again for joining me, and I hope to see you soon in the workshop. Take care.